Thank you. Now, I really want to thank all of the organisers for putting together this amazingly stimulating meeting. I feel very much among friends. I feel positively encouraged to try out thoughts that I might be more reticent about expressing elsewhere. So I hope you'll take this talk in that spirit. And I really wanted to thank Johannes and Robin for everything they've done over the last couple of years to stimulate interest in this field. I know it's had a really big effect on the physics community that I'm part of, and I think on other communities too. So I should start by locating myself as far as I can in the landscape of conference attendees. My own background is a mathematical physicist. I think about consciousness as in the end, a problem in fundamental physics. The problem being, how does matter, which we certainly don't understand at all perfectly, but we understand pretty well, how does matter give rise to consciousness? And mathematically, how do we characterize that in a law-like way? And I stress the law-like because I'm aligned with David Chalmers, many other people, including some reasonable fraction of the people here, but I appreciate not by no means everyone, in believing that there is a glaring explanatory gap between the known laws of material physics, quantum theory, general relativity, and so on, and the phenomenon of consciousness. So, one way, I'm persuaded, at least one way of highlighting that gap goes back to a beautiful paper from 1879 by William James, this with the title We Automata, published in the journal Mind. And the path I want to take into the explanatory gap and tentative exploratory ideas that might help some way towards bridging it is to think about the relationship between consciousness and Darwinian evolution. So these extracts are all from James's paper, and I've tended to highlight the more significant quotes in red. So the first one I think is just beautifully expressed. Feeling is a more collateral product of our nervous processes, unable to react upon them any more than a shadow reacts on the steps of the traveller whom it accompanies. Inert, uninfluential, a simple passenger in the voyage of life. It's allowed to remain on board, but not to touch the helm or to handle the rigging. Of course, William James was Henry James's brother, and it's often been suggested that William James was the better novelist and possibly Henry James the better philosopher. Certainly the right. And James particularly focused in this article on what he saw as, in modern day terms, the problem that inversion of the qualia seems perfectly logically conceivable. So if pleasures and pains have no efficacy, one does not see, if they have no efficacy, one does not see why the most noxious acts, such as burning, might not give a thrill of delight, and the most necessary ones, such as breathing, cause agony. If consciousness is just coming along for the ride, then it has no effect on the actions of our material selves, and it doesn't matter whether we enjoy stuff that's good for us and hate stuff that's bad for us, or vice versa. That, in a nutshell, is the problem he was trying to probe. So I'm not confident. I mean, James's own views on consciousness evolved, and they evolved in a way that I find confusing, and I'm not competent to review them. But he certainly carried on pressing on this point for some while, and in the Principles of Psychology from 1890, he again stresses this gap between our material understanding of the world and then the dawn of consciousness, where an entirely new nature seems to slip in. Something where the potency was not given in the mere outward atoms of the original chaos. And there's this quote that seems, in the light of quantum theory and its indeterminism, possibly prescient. The performances of a high brain are like dice thrown forever on a table. So a high brain, something like the consciousness that's steering us. Unless they be loaded, what chance is there that the highest number will turn up oftener than the lowest? Unless something is affecting, and so again, I'm translating into modern thought. Unless something is affecting the quantum indeterminism, something to do with consciousness, it isn't doing any use. It doesn't seem to be of any use. And if it's not of any use, James argued, and I'm going to try and review the argument, it's hard to understand how it's evolved to have the properties that it has. So, needless to say, there are problems with this view. It's one thing to point out a problem. People said at the time, and still many people would say, it's actually a pseudo-problem. But even if it's a genuine problem, it may not be a solvable problem. There may just be nothing scientifically useful to be said. Certainly there's a real conceptual barrier to making progress. And this is from Charles Mercier's Nervous System and the Mind, already pressing James on this point. How is something like the idea of food supposed to prevent stuff happening in the brain, some molecule decomposing into two smaller molecules? It can only do so by increasing the force which binds the molecules together. Good, okay, so try to imagine the idea of a beefsteak binding two molecules together. It seems like one of Chomsky's sort of meaningless sentences. It's grammatically correct, but it's impossible. And James's response, a charitable view would be, especially in the light of quantum theory, that a lot of what we understand about matter and binding and so on doesn't really fit intuition. And maybe a more critical view would be that he doesn't really answer that point. He just deflects or tries to deflect attention from it. He says, well, that could be a problem, but here's another problem. Let's worry about the other problem and pretend that we didn't notice the first one. So the whole idea of binding is a mystery. I don't know. I find James a little less persuasive there than in the earlier quotes. So James, of course, was writing before the development of quantum theory, and although he was a distinguished psychologist before modern neuroscience, but it's certainly not the case that his arguments have lost all traction in the light of modern physics or modern neuroscience. People who are deeply familiar with both subjects have done a lot of research on both subjects. Alex Cairns-Smith, Ian Glynn, Graham Mitchison, to mention just three, have worried a great deal about James's arguments and have found them just as compelling, given what we now know, as they seemed to James when he was writing. And indeed, the idea that there's something puzzling about consciousness and evolution has been taken even further, even more provocatively, in a much more recent book by Thomas Nagel, Mind and Cosmos. For a long time, I found the materialist account of how we and our fellow organisms came to exist hard to believe, including the standard version of how the evolutionary process works. And yeah, the provocations start early and they keep on coming. And I'm only going to quote from chapters 1 and 2. Believe me, they keep on coming. For people who haven't read it and you want a bracing argument that the world could be nothing like the way you thought it was, whether or not you're persuaded, you might enjoy confronting his arguments. My guiding conviction is that mind's not an afterthought, ... but a basic aspect of nature. And Nagel strongly suggests that we need something beyond the existing laws of physics. We need some form of teleological principle or law. And this is an intriguing quote, again, given quantum indeterminism. Teleological laws would assign higher probability to steps on paths that have a higher, scare quotes, velocity towards certain outcomes. I'm not confident that this Aristotelian idea of teleology without intention makes sense, but I do not at the moment see why it doesn't. So first I want a caveat. The full title of the book is Mind and Cosmos, includes the subtitle, Why the Materialist Neo-Darwinian Conception, blah, 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 is almost certainly false. That's Nagel's view. It's certainly not mine. Nagel has some, well, I don't want to get too sidetracked or to try and represent him, but he has some sympathy, which I don't share, for critiques of Darwinian science, even aside from consciousness. To me, there's the problem with consciousness, but everything else seems very plausible, very uncontroversially plausible. We have a list of steps, starting with finding the right star system that has organic matter, through something like this series of things to us. We don't know the probabilities of each of these. People have worried that they're so embarrassingly small that it's incredibly unlikely that we would have evolved, but I don't think there's any compelling case for that. People have also worried that they're so embarrassingly large that aliens should be visiting us all the time, and the fact that they don't suggests there's something wrong with this whole picture. I think, for me at least, Sandberg and Drexler and Ord have looked into the Fermi paradox quantitatively and argued pretty persuasively that you can't argue on the basis of what we know that the probabilities are embarrassingly large. They could plausibly be about the value that there would be only one civilization within causal contact to ours. So I'm not worried, certainly not in this talk, about the Fermi paradox. I'm not worried about anything else about evolution except consciousness. But I am worried about consciousness, and there's a worry that there's an interesting question, I guess, which interests everybody, which is, where does consciousness fit into this ladder? Here or here or here? And associated with that, a more controversial question, does it affect this chain of probabilities? Does the fact that there's this phenomenon of consciousness alter the chance that starting from this, you end up with something like this? So here, for me, are four what seem like serious puzzles for the materialist account of evolution given consciousness. And the first is why? Yeah, why are we even here and talking about this? Why are we conscious at all? And the other three you can think of, and as a physicist I tend to think of, as fine-tuning problems. If you take the sort of perspective that James does on the relationship between mind and matter as your starting point. If mind is just coming along for the ride, why does it have the property that we're able to talk about it? Why can we report the contents of our consciousness? Why does the word consciousness appear in the dictionary? Why is our consciousness so focused on evolutionary salient features of what's going on inside us and outside us? Why, and this is James's question precisely, why are evolutionarily advantageous activities pleasurable and disadvantageous ones painful? And the reason why these seem to people and people with whom I'm aligned to be problems is essentially the conceivability argument. It seems perfectly logically conceivable that there seems to be a map from matter states to mind states, and in particular from brain states to mind states. It seems perfectly logically conceivable, given what we understand at the moment, that that map could have very different properties. And it also seems logically conceivable that, given what we understand at the moment, if it had very different properties, it wouldn't affect the standard materialist account of evolution. In fact, that last bit is more than logically conceivable. It's simply a statement of what we understand at the moment. The map doesn't affect the dynamics of matter. So it seems logically conceivable that we could have no consciousness. We could be philosophical zombies. It seems logically conceivable that we could be conscious, have active mind states of some sort, but be completely unable to express them. That we could be dilettantes in the cosmos who are conscious of stuff that was nothing to do with whether we survived or not, but entertained us for whatever reason. And had no control over that. Or, as James suggested, we could have pleasure pain qualia inverted, or just uncorrelated with survival value. It could be just met a random thing, whether you found something pleasurable or painful. In each case, on the standard materialist view, our behavior wouldn't be affected, and so our evolutionary history wouldn't be affected, and so you could run the same story about the plausibility of evolution, but with very different features of consciousness from the ones that we find. And from my perspective, this seems, in the end of problem for fundamental physics, the same sort of problem as something like the cosmological constant problem. It seems logically conceivable that the cosmological constant could take very different values, or indeed the electron mass could. It wouldn't contradict everything else we know. Maybe the electron mass is just given to us, but the cosmological constant seems to have a special value. And so we're bothered by the fact that it's not logically required, and yet somehow it is extraordinarily close to zero. That's a fine-tuning problem. These seem like much more detailed and so much worse fine-tuning problems to anybody persuaded by the power of the conceivability argument. So emergence has already been touched on and indeed argued over in earlier talks. People have used Chalmers' terminology, which I think is a good one, that we distinguish between strong emergence when high-level phenomena, in particular consciousness, arise from a low-level domain, but we can't deduce truths concerning it from truths in the low-level domain, the low-level domain being the materialist physics that we understand relatively well. Weak emergence, it can be very hard to deduce, but in principle, at least, it's deducible. I agree with Chalmers that in our current understanding, consciousness appears to be strongly emergent. So we have a relationship like this, quantum theory. Actually, I think it's also true that classical physics is, in our current understanding, strongly emergent from quantum theory, but that's not the subject of this talk. Darwinian evolution works perfectly well given classical physics, but we have a strong emergence running here and here. And you could think various things about strong emergence, but again, as a physicist interested in foundation, it seems to be a pointer to the fact that we're missing laws. There should be some further laws, some better theory, in which we can replace these strong emergent lines by weak emergent lines. Well, so I want to look at the logical space of possibilities, not because I want to advocate them very strongly at the moment, but because at least they're there and they seem worth exploring. And it's worth asking ourselves whether or not they could give any additional explanatory power beyond the physics we have. So the sort of theories I want to look at are they're indeterministic, but they're not Markovian. They're generalized probabilistic theories. They're interesting anyway. They're independently motivated when you think about quantum theory in the context of cosmology, and I've written about that from time to time over the years. This is the most recent article, but this one goes back to 97. But they're also useful for this task, where we have a phenomenon that seems to be strongly emergent, and we're wondering whether changing our fundamental theory might bridge that explanatory gap. So I want to illustrate the key idea of these theories with a very well-known model in statistical physics, the Ehrenfest model, and if I can get a demo working, I will. Good. Okay. So this is a very simple way of thinking about and illustrating the properties of entropy. The idea is we've got, in this case, 100 enablables, and at each time step, one random number from 1 to 100 is going to be chosen, and the corresponding ball is going to move from whichever n it's in to the other one. And we're well, at least in this iteration, we're interested in understanding how originally relatively ordered states become disordered, so how entropy increases. So we're going to start with 3/4 of the balls in one urn and 1/4 in the other, and just run step by step. Balls are going to move across. Following the individual balls isn't very helpful, but you could see these two lines, as you'd expect, converging, and if we let it run for long enough, we'll get roughly 50 balls in each urn, and it takes a while to converge. But it gets there, and it takes a very, very long time indeed, much longer than we have, for it to start diverging again and getting back to 75, 25, let alone 100. So, although actually it's giving it a go there, but no, it won't succeed. Okay, so that's the standard model, and that's the analog for standard quantum mechanics with the initial conditions fixed, and then unitary evolution and some randomness coming from measurements. Sorry, I need to kill that. And go back to slideshow. Okay. Press, sorry, which one?
From current slide, just to the left.
From current slide.
Second from the left. Your left.
Left?
More.
Ah,
There you go.
beautiful. Yes, thank you. Okay, so you can produce modified versions of an Ehrenfest urn model just by making up your own rules. So one way of doing it is to take a lot of runs, you've got a whole ensemble of runs, and then picking out the first one that satisfies some particular condition. So here I've done this until you get exactly, you started with equal mixing and until you get exactly equal mixing halfway through and again at the end. Here I've done something else. I picked a big ensemble, but then given each of them a probability weight that depends on how close they are to this line. So this line starts at equal mixing, and after 20 steps, if you followed the line, you'd end up with all the balls in one urn. How close they are, well, I've taken this measure, so the difference between that the square of the difference between the number of balls in that line, and we sum that over each point, and I put in a factor of 6 because that's about what I needed to get it to converge in reasonable time. So you run, and then with this probability, you choose that line. So most of the time you don't choose it because this probability is rather small, and the one that tends to be selected is going to tend to be relatively close to the line. So there's actually, although they overlap, 5 different things here. And both of these are evolution laws, but they're not evolution laws that are determined only by an initial condition plus randomness. This one has fixed constraints. This one has a probabilistic constraint that makes the model tend to follow a particular path. So this first one isn't super impressive. You get something like this. There's about a probability of 1/4 of getting this by chance, and so a 16th of getting it twice. On the other hand, if you ran this a lot longer, say 200, and every step of 10, you found an equipartition, the probability of that occurring by chance would be very small, and so you would think there has to be something else going on, and if you wanted a theory, so to speak, of what your own model was doing, you'd probably produce this rather simple theory that it's just constrained so that every 10 steps it goes to equipartition, and otherwise it's random. These things may look relatively random, but they're actually very far from random. It takes about 50,000 or so iterations to pick out one of them. So if you do find something like this, your best theory would be something like this probability-weighted version. Something is causing these things to try to approximate this weightless line. You might not know exactly what the weight is, but you'd look for some formula, and this is a reasonably simple sort of formula. With more data, you might get better. So we need to distinguish these ideas. We need to distinguish teleology, in which just the final state is constrained as well as the initial state, from less common word, hodology, in which the model is constrained to maybe not to precisely follow a path, but constrained towards some particular path. And we need to say something about quantum theory, and to do that, we confront the quantum measurement problem or quantum reality problem. We need to say what quantum probabilities are probabilities of. That's a fascinating topic, which many of us are interested in, but it's not what I want to get into here. I just want to assume that we've got some answer to it, so that in Bell's terminology, we have decided on some set of beables, the events or the trajectories or the point-like flashes associated with collapses, as in, for instance, the Penrose-Hameroff model, that quantum theory determines the probabilities of. We're going to take that for granted, and then we're going to look for laws that modify those probabilities, or at least think of that as our ultimate motivation. And then I want to introduce some toy models that explore what you can do with modified probabilistic laws, that are taken from Cellular Automata from Stephen Wolfram, the book by Stephen Wolfram and his collaborators. I seem to be crossing out a lot of book titles today. So Wolfram's book is intriguing and enjoyable. I don't understand in what sense it's a new kind of science, but it's great for what it is. So here's the game I want to play. I want to explore the idea in toy models that local probabilistic dynamical laws from microphysics, the sort of thing we have from quantum theory, could be locally modified when specific physical configurations, and I'm having in mind that those could be whatever turn out to be the neural correlates or the physical correlates of qualia, when they arise. We're going to try and do this with toy models defined by probabilistic cellular automata, because at least you can say something definite with these, and they illustrate the idea. And the particular automaton I want to look at is given by Wolfram's so-called Rule 110. It's a very simple automaton, but it has very rich structure, and in particular, it's Turing complete, as Cook proved in 2004. Any computation that you want to do, you can do within this automaton. So at least in that sense, it's a good toy model for cognition in the form of calculation. How does it work? How do we think about this thing? Well, everywhere on this slide, and I think in the rest of the slides, time goes downwards from the top. So the automaton is built on a discrete square lattice, and it has periodic boundary conditions, so this is identified with this. And we start by determining the top row, and each square can have two states, 0 or 1, black or white. And then the next row is determined, so each element of the next row is determined by its three predecessors, the one above it and just above to the left and above to the right, following these rules. So these three, if you have these three states black, then that one there beneath them is going to be white. These three are white, that's going to be white, and these things. Okay. It looks like a fairly unremarkable set of rules, but this automaton turns out to have particularly interesting properties. So here's one of them. You could find regular arrays, such as this one, which just continue forever, propagating according to this rule. See, and I want to think of this as something like a vacuum or a background state in our toy model. This isn't unique. There are other stable periodic structures, but let's focus on this one because it happens to work nicely. Okay, so we have a background. We have a sense of what it means for nothing to be there. And then there are so-called gliders. So if you have a little dislocation in your initial, in your first row, some bits take a different value, or you insert a little sequence of bits of the right type, you could create a structure that propagates regularly, as you can see this one doing, or well, this is much larger insertion, but this one also slightly more complicated, but propagates regularly, and it does it forever. And here's some more of them. There's a classification of a large variety of these, including some infinite classes. There are also, but I'm not going to use them, things called glider guns, which behave like this, but they also spit out more gliders from time to time, like decaying particles, but decaying particles that can keep on decaying and producing new products. And here's a whole set of them. They all go with their own characteristic velocity, and they've been arranged here so that the fastest moving ones to the left are on the left, and the fastest moving to the right on the right. And you could see some series, so this and this and this and this all belong to the same series, for instance. Good. So what? Well, let's just carry on with glider phenomenology for a little bit more. Another nice and intriguing thing they do is undergo things that look rather like particle interactions, following things that look a little bit like Feynman diagrams. Although, of course, this is a classical model, and you don't sum over these diagrams, you just have one for each interaction. So, for instance, this glider and this glider, if they start just here and here, go through a little bit of a chaotic phase, and then it turns out they propagate on. This one is continuing down there, and this one down there. But that doesn't always happen. If the displacement's a bit different, then they produce this single one. And another different displacement, well, that still produces that one. And now they do something else, a couple of different gliders. All right. And now, what if we start perturbing? Well, suppose we've got the ether, this background, and we've got a glider like this, or this, or this, or this. And we have some sort of errors, little perturbations of the initial state. So maybe just one bit is flipped somewhere over here. Well, if it's far from the gliders, what tends to happen is that it produces ripples, so to speak, in the ether for a while, and then they fade away, and the glider goes serenely on, and the ether goes serenely on. So in the long run, they make no difference if they're rather far, relatively far from the glider. So that, again, these are the perturbations far from the glider. But now suppose we do it close to the glider. It can make a dramatic difference. So here's this glider, and now I've perturbed a bit right next to it. Well, now we get two gliders, and neither of them is the original one. In fact, you've got this quite complicated one. This one actually survives unscathed, fortuitously. This one's broken up into 3 different gliders. This one's got 4. This one's got a couple. So only one of these survives unaffected by a perturbation in the place that I happen to choose it. So why am I doing this? What use is it for a toy model? Well, I mean, the word toy cannot be underlined enough, so please sort of stretch your credence and imagination as far as you're willing. But I want to think of this as a toy model for a physical substrate. In other words, I want to think in a very loose sense of the ether as the analog of a brain, or something like that. That substrate is built out of elementary physical quantities. These are the elementary bits in the grid, in which you could get more complex and relatively stable structures. These are the gliders. And I want to think of the gliders as the analogs in this model of whatever turn out to be the neural correlates of elementary conscious qualia. So the gliders are supposed to be the neural correlates of qualia. The complex structures, the gliders, unlike the elementary components, have both a physical aspect, they live here in this model, but they also have a mental aspect. There's an associated quale with each one of them. And I want a probabilistic model because we want to play this game of modifying probabilities. So to simplify things, I'm going to assume that all the errors, any error will occur in the initial state, and the only rule that we have to start with is that there's some chance p of an initial bit being randomly flipped, so that it's the wrong thing. Obviously, if we were really trying to mimic quantum randomness, we'd have flips everywhere, but that would just complicate the illustration without really changing the point of principle. So let's assume all the flips are in the initial state. Okay, that would be something like our model with standard quantum theory, but we want to modify the probability rules, so we want the probability rules also to depend on the gliders. And the first modification I want to look at is a rule that says single gliders are robust. In other words, if you start with glider G in the initial state, there's a probability very close to 1 that the final state will contain glider G. So if that rule is imposed, we no longer have a uniform probability of errors occurring in each of the initial states, because any error that occurs has to be, if this is very close to 1, has to be consistent with this second imposed rule. So we can only get a flip at points, at sites that aren't going to affect the final state containing glider G. And that should be fine if the flips are far from G, but we're going to get suppression of bit flips of errors, in other words, close to glider G in this model, unless fortuitously they happen to be things that don't affect the glider's propagation. But generally they will. So generally, imposing this rule means we've replaced a uniform probability of bit flips by a probability of bit flips that's not much different away from G, but almost zero probability in the region of G. Okay, and we can think of, instead of thinking about a single glider, we can look at what perturbations do to interacting gliders and then have the same sort of implement the same idea of a toy model in which our probability rules are altered. So I've got the same glider interaction, and I'm just a sequence of sites in sequence, 21 of them, where the initial bit is flipped. So first there, and then there, and then there, and then there, and it carries on through all of them. And if you look at this list, 1, 2, 3, 4, yeah, six of them actually leave the final state unscathed. The initial error doesn't do very much. And the rest of them change it, often quite radically. And it's also interesting to note that some class of them, there are classes of them that produce the same output, but it's different from the unperturbed output. So for instance, this and this and this all end up producing, although in different ways, this single glider. So if we think of a toy model involving interactions, we want the same idea that there could be a probability P of any initial site flipping, but we want the probability rules also to depend on the gliders, and we're free to make our choice. So one thing we could do is, again, demand robustness. If you start with G and G prime, then there's probability very close to 1 that you end with G and G prime. And so now you have to recalculate your probabilities of bit flips, and they change. We're only effectively going to suppress all the bit flips that take us away from G prime and only keep the ones that leave them there. So the probability of initial bit flipping is location dependent, has chance still close to p if it's far from both of them, because it will peter out. And it's in a few key locations that don't affect G and G prime. But for chance 0 of flipping in locations that do something like this, that alter the final state. That's allowed, that's forbidden. If you want a cartoon sort of, so I suppose these are not elementary qualia, but collections of qualia. But if you want a sort of cartoon version of what this is supposed to be doing to collections of qualia, something like this, that the dynamics ensure that if you start with the thought, Joe is my friend and I would like a hug, and there's a little bit of an error somewhere in your brain, it should be robust. So you end up with a very high probability at a later time, still with the thoughts, I would like a hug, Joe is my friend, possibly in the other way around, since these things do cross over, but that's the extent of it. And you certainly don't end up with something like this. Joe is my friend, I would like a hug does not, just is not allowed to be made through a bit flip error into a whole sequence of different glider qualia. Giraffes are blue again. I need to go skydiving. My friend Mary turns out to be an alien. That should not be happening. We can also, we could do more, possibly more interesting things than ensuring robustness. We can make the dynamics ensure glider interactions that would otherwise have very low probability. So for example, we could just impose as a modification of the probability rule that if you start with G and G prime, you should end up with some specified glider G double prime, which is a possibility if you get a bit flip in the right place. But now this is allowed because the bit flip just here just turns out to produce G double prime. But this one isn't allowed because it doesn't, it actually leaves them alone. And no perturbation isn't allowed either. So with this modified rule, you ensure that there will be some error, although maybe error isn't the right way to think about it now, and that it will be in the right, one of the few correct locations to convert G and G prime to G double prime, something like, Joe is my friend, I would like a hug. I must have been in a slightly warm-hearted mood when I wrote this slide. So you say, Joe Bear, have a hug. All right, what if anything do we take away from these obviously cartoonish, extraordinarily cartoonish toy models? We've got some higher level structures. We're supposing there are some higher level structures, and in particular things that that arise in brains that have a dual physical and mental aspect. We have to do that to have any interest in these models. Well, that doesn't seem to be the weakest point. There is some argument for this, since brains themselves have a dual physical and mental aspect. Reductionism suggests that something smaller than brains should. If you go all the way to panpsychism and every elementary particle has a quale associated with it, you have all the problems of panpsychism. And well, that's a whole other discussion, but it's not obvious that that's the most fruitful way to go. But otherwise, something intermediate has to fill the role, and so we end up with something like this hypothesis. We've shown in these cartoon toy models that modified probabilistic laws allow these dual structures to have causal power, and that causal power is not entirely dependent on the elementary laws governing the elementary matter. In other words, if we understanding the rules of the cellular automata, and even understanding the probabilities of errors absent our modifications, does not explain the causal power that the gliders come qualia have in these toy models. We can define qualia dynamics with their own laws, which are consistent with, I mean, they adapt the laws that are there from the substrate, but they're not determined by the microdynamics. They're not determined by the cellular automaton. Yet together they form a consistent unified model. That may be a weaker well, that may be a more worrying thing to thought to entertain. There's a weak argument in favor of it, which is if we've agreed that something's got to be singled out as having both a material and a mental aspect by laws of nature, well, it's already playing a special role in nature, and then it arguably at least seems natural that it should also play a role in the dynamical laws of nature. And if you want a wild speculation, perhaps if it makes sense to talk about the reason why nature is random, why do we have probabilistic laws, perhaps it's to do with this need to combine dual causalities, or causalities on different levels of matter and mind. Obviously, it's much simpler to assume that mind states just come along for the ride, epiphenomenalism. It may be correct, it's not logically contradictory, but it does leave all the evolutionarily adaptive properties of consciousness a deep mystery, as William James pointed out, and with arguments that I and others still find persuasive. The toy models show that there's at least logical space for reducing that mystery. The evolution of consciousness becomes less mysterious if dynamics give it a genuinely causal role in behavior. The rest is sort of a sketch of ideas, no more than that, but you can imagine a story about evolution where you have this dual form of causality which it's made use of to create more stable stimulus response circuits or to follow higher level reasoning than the elementary dynamics would. But two causal structures, so to speak, are more adaptive than one if they evolve to interplay in the right way. Arguably, and I don't quite know even what I think about this, but arguably, James's puzzle about the correlation of pleasure with advantage and pain with disadvantage is explained or partially explained in these models, in the sense that a pain just is the sort of thing a mind attempts to avoid. If you have a dynamics of qualia, arguably by definition, it's a dynamics in which pains are things that are being suppressed. I'm not sure. Anyway, there's food for thought there. It still seems, to put it mildly, a fortunate coincidence, even if you take these sketchy ideas seriously, that not only is there proto-consciousness around in the universe, but it happens to be in the right form that evolving life on Earth, for example, was able to create it and then exploit its properties. The only thing I would say about that is we do have life on Earth and it is conscious, and it's not clear to me that there is a conceivable form of a better explanation than that. This may be only a partial explanation, but not everything. In the end, there are brute facts. Not everything has a complete explanation. It may be my failure of imagination, but I don't see how much better one could do. Obviously, these models are so crude. They're meant to hint at more sophisticated ones in which we can see creatures evolve via modified dynamics. And they say something that's, at least in principle, is testable about individual organisms. If you take the idea of this model seriously, then it's not just that the dynamics that describes the evolution of life on Earth is subtly different, but the dynamics of this, basically each and every organism on Earth is, over its lifetime at least, subtly different from those predicted by quantum theory. And perhaps not just over its lifetime, but even over its typical cognition time, if this is a really serious effect. Okay, I could say a lot more, but I'm going to spare you everything except closing quotes. I keep trying to stress that I'm in sort of speculative and exploratory mode. I feel encouraged by the organizers. The best one I think one can hope for sort of these ideas is that they follow Samuel Beckett's maxim, which is even written in this river here, of failing, but failing a little bit better. It's a start. And I just wanted to close with one of my favorite quotations. One of the many great things about this conference is it brings together people who are absolutely fascinated by consciousness, of course, but by nature in general. And this quotation reminds us all to hold on to that fascination, not to become blasé about anything, about the night sky, about the fact that we can see the night sky. So I'm grateful for having that reinforced by the meeting as well as everything else. And with that, I'd like to thank you and invite questions.